Hi everyone, my name is I'm happy to present our paper today, Practical Privacy Preserving K-means Clustering. This is a joint work with Payment Mohasho from Facebook, Microselect from Oregon State. This work is partially done when I work at Oregon State and Visa Research. So why do we consider this problem? The first question is what clustering is? Well, clustering is an unsupervised machine learning problem. It's allowed to group similar or closer items together. In this scenario, we have several points and we want to group them into three clusters. And here we have a red a group, a blue, and a green one. And now, why do we consider clusterings in the context of privacy preserving manner? The reason is that machine learning problem as well as clusterings is data hungry, but the data might come from different sources and very sensitive. For example, Visa, US Bank, and the Bank of America, they all have transactions. And they want to cluster on the union of their database to analyze some information. For example, they want to find out fraud detections. However, they can't share that database to each other. In other words, we want to run clusterings while keeping their data private. In this work, we consider two server models. This is a very popular setting in private work on secure machine learning. And here, the data trainings are secret shared by two servers. Therefore, if two servers do not collude, they don't learn anything about the original dataset. And now the servers run two-party computations on the shared values and output the models. Compared to previous work, our scheme is more efficient and scale to the big dataset. So there are two popular clustering algorithms. The first one is K-means clustering, and its complexity is dataset size times to the number of clusters times to number of iterations. And hierarchical cluster is the second one, the second popular one, which the complexity n square log n, and here n is the data sets, and it's much larger than the number of clusters and number of iterations. Therefore, clustering is faster than hierarchical clustering, and it's widely used in many applications. So this talk and this work we focus on K-means clustering. So as I mentioned before, K-means clustering is the popular machine learning problems. However, there are very few works focused on it. So some of previous work, they doesn't provide the full privacy guarantees. So for example, they review intermediate cluster centers. Another works are heavy on public key operations and require homomorphic encryption for each item. Therefore, it's inefficient when the dataset is big. In this work, we provide the full privacy guarantees. Our scheme is based on symmetric key operations. So we propose efficient secure Euclidean distance. We also customize minimum circuit on the shared values and propose the efficient K-means clustering protocol. As a result, we show that our scheme is 5 order of magnitude faster than previous work. So I will go through our uh, privacy preserving K-means clusterings. And as I mentioned before, the input is secret share between two servers. And through my presentations, I use notation square bracket for the shared values. And the input also includes the number of cluster M here. So for the protocol, the first step is to choose a random cluster centers. Here we have 3 cluster centers, a red one, blue one, and a green one. So now the protocol is for each data point DI and for each cluster CK, we need to compute the distance between DI and CK. So it means that here, for example, we have we choose this point and we need to compute distance between this point to C1, to C2, and to C3. After having the distance, we will find the closest cluster to this point. So as you can see, we have a long green distance, a blue distance, and a short red distance. And the last one is closest to this point. Therefore, we assign this point to the red cluster. So it means that we will call this point as a red. And now we similarly we can color all the red points, the one closest to the red clusters. And we also color all the blue point, the ones closer to C2, and the green points. So after all the points assigned to each clusters, we compute the average of these points within clusters. So for example, we need to compute the average of all the red points, and it's here, a yellow cluster. And we need to update the current cluster to the new one. So you can see the red move to the yellow one. We repeat the whole process until clustering converges. So it means that until the red cluster move to the correct order, the green, the blue, and the green one. And note that all the data points and cluster center are secret shared between two servers. So this is during our scheme. And now we have some questions we should address in privacy preserving clustering. The first question is how to compute the distance. I mean, for example, Euclidean distance efficiently. So it means we want to compute this one, right? A second question is how to find the shortest distance. So how to find the K star and how to assign the value to the corresponding cluster. And the last question is how to obviously update the cluster centers. So for the rest of my talk, I will tackle these questions. So for the first questions, I'll present our secure Euclidean distance. So as you may know, given 2 points, their Euclidean distance can be computed by this formula. And here D and C have L dimensional vector. And for example, if L equal to 2, so we have the distance between C and D equal to D1 minus C1 square plus D2 minus C2 square. So we note that in our work, each party holds the share of the DI and CI. So it means that DA and CA known by Alice, and DB and CB known by Bob. And therefore, we can rewrite the distance by put all the A value one side and all the b value on another side. And now we express the square equation to this formula. So clearly you can see that Alice knows all the red values, and C can locally compute the first terms. And Bob knows the blue values, so C can compute the second terms. So the main thing here is Alice and Bob need to jointly compute the sum of inner products, where Alice knows all the red value and Bob knows all the blue values. So pivot work, they use generic inner products. And in this work, we observe that first we need to compute the inner products between one point to many clusters. So remember that we have, for example, we have 3 clusters. You need to compute the distance between this point to another 3 cluster centers. And the point here is, the data point here is fixed during all the iterations. And number of cluster is much smaller than number of data points. So we rewrite the sum of inner products by this formula, where we put all the dA on one side, all the dB here, and CA times CB. And then we use inner products based on Oliver transfer. I won't go to the detail how the inner product space of Oliver transfer work, but the main key here is when you rewrite the inner products by this formula, you can reuse the OT for dA when compute the first terms. You can reuse OT for dB when compute the second terms. And the last terms is very efficient, is very cheap because the number of clusters is small. So our experience show that our secure Euclidean distance is 32 to 150 times faster than private work. So we are done with the first questions and go to the second questions. Now the input are the shared Euclidean distance between the point and many clusters. And our goal here is first we want to find out the closest distance. So K star here. And we will assign the point to cluster centers. So most of previous work, they review K star, which lists significant information about data training. And in this work, we hide K star by present K star as the binary vector. And the vector here is size of M, and M is number of clusters. And the vector has all zeros except for the position K star. So it means that the number 1 here indicates the index for the minimum. And again, all the parties hold the Boolean shares. Both parties hold the Boolean share of the values. And we use the Gabor circuit to compute this vector. So we note that Euclidean distance have the arithmetic shares. And to use the Gabor circuit, we need to use a Gauss shares and convert from arithmetic share to Gabor circuit to Gauss share is not cheap. So in our work, we propose a customized Gabor circuit for this problem. So please see the paper for more detail. Yeah, so we are done with the second questions. And now we'll go to the last questions, is how to obliviously update the cluster centers. So first, we need to securely compute an average of all the points which are belong to clusters. So for example, here we have all the red points belong to the red clusters, and we want to compute this point, a yellow one. So from previous steps, we has the bit vector indicate which data point di is in which cluster ck. So in this slide, we have d1 and d3 belong to ck. So when we look at the vector, vertical vector mk, the average can be computed by this formula. So as you can see, d1 and d3 are included in the sum because the number are number one, right? But d2 and dn isn't because it's 0 and 0. And all dm and di secret share among two parties. So we can rewrite the formula by that one. And now the direct solution is to convert the Boolean shares to arithmetic shares and use the secure multiplications. However, we have a better solution based on oblique transfers. So please see the paper for more detail. Yeah, so we are done with all the questions. And now I'm going to the performance of our scheme. First, we are interested in performance comparison of Euclidean distance with Manhattan and chessboard distance. So the Manhattan distance between 2 points are the sum of this one and this one. And the chessboard distance is the maximum of this and this. So therefore, the two metrics are considered as the alternative distance metrics in some machine learning applications. And from the formulas, which are considered privacies, you can see that computing Euclidean distance is expensive than others because it involves more complicated calculations. However, our experience shows that our secure Euclidean distance is 10 to 40 times faster than Manhattan's and chessboard distance. The reason here is the cost is amortized. And in our Euclidean distance, we can reuse the OT to compute that one. While in Manhattan and chessboard distance, you need to compute the maximum and minimum inside the secure computations, and which are not efficient. We also show the performance of our K-mean protocol. And from the table, you can see that our scheme requires 20 minutes to compute 100,000 points into 2 clusters. And in terms of communications, usually the symmetric key-based protocol require more data transfer. We also show that our scheme is efficient when increase the dimension of data set. And for the accuracy, our privacy-preserving K-mean clustering achieves almost the same accuracy compared to the plain text versions. Thank you for listening, and you can find our paper at ePrint and the code on GitHub.